however, and so we'll kind of get to those. But yeah, that's a great question, because I think questions are the main point of what we're doing. So I first wanted to talk about some of his pioneering work in the early 90s. So this is 1993, a Nature paper where they talked about standing waves in two-dimensional electron gases. And basically what this was is STM measurements of this copper surface in an ultra-high vacuum at 4 Kelvin. And they found these really interesting kind of phenomena that were appearing in the structure. And so we can see that kind of broken down a little bit here. So I wanted to highlight some work that was done a few years earlier by Everson, where they observed kind of some similar things in this kind of differential conductance versus sample voltage measurement. So you can see, you know, the one on the left is kind of flipped from the one on the right. But basically what they're showing is this kind of increasing kind of local density of states with the voltage bias, yet there's this cusp around, you know, 0.5-ish volts, where we get this kind of drop in that differential conductance. This kind of harkens back to some theory in the 70s where, you know, where they were studying these band structures and looking at the kind of surface states of these band structures, and they found that with the hybridization of the kind of SP and D bands in these FCC transition metals, that there was this ability for these surface states to kind of tunnel in and out of this kind of like hybridized surface band. And so that cusp actually corresponds directly to that bottom of that surface band, which is really interesting. And we see that in both cases. However, in Dr. Crommie's work, we're seeing more of these oscillations, which is likely due to the experimental conditions and the fact that, you know, the Everson work being at room temperature, likely encountering some quantum phase decoherence and maybe inelastic scattering or instrumentational limitations. So first of all, you know, this work by Dr. Crommie in the 90s was really fine-tuned and able to kind of, you know, look at these very small oscillations. And then when we look at kind of a more spatially resolved picture of this differential conductance, we can really see that oscillation, that oscillatory behavior, the standing waves become much more apparent. And so you can see at these different bias voltages, which are kind of juxtaposed vertically, we can see that the wavelength not only increases as you bring that voltage lower and lower, but the magnitude of those oscillations increases until you get to that kind of 0.4, 0.5 region where once you jump from negative 0.4 volts to negative 0.5, that magnitude kind of collapses. And that corresponds directly with the figure that we saw in the last slide, where we have that kind of cusp at around 0.4, 0.5. So in the interest of time, I'm going to kind of, you know, highlight that, but move kind of to the next slide. Sorry. So I wanted to talk really briefly, you know, as a theorist, I wanted to just mention some of the modeling of these kind of surface states, because as we can see here, the theoretical kind of waves seem to match very well, and that fitting is really interesting. It's done just via a hard wall potential, and that step edge can then be modeled as kind of this hard wall potential where we get this scattering of these standing waves, these electron states scattering along that hard wall potential. The point impurities are modeled via a cylindrical scattering potential. And so there's some really interesting stuff going on there. But the main point is that we're seeing these standing waves. And I think this leads perfectly into the next paper that I want to discuss. So I'm going to
wait, go.
Oh, yeah,
I'll
go ahead.
I'll just say this is my great theoretical contribution, that LDOS formula. I actually derived that, and that's like my one derivation that I actually did on my own. Well, a theorist told me to look it up in an integral book, in a book of integrals, you know, to get that Bessel function. But that's like my only theoretical contribution that anyone actually uses.
Well, that's great.
Maybe I'll also mention just that this this ability to see these waves, the whole, I just want to make the point that it's really because of Don Eigler, who was the first to make a low temperature STM, and that's why other people hadn't seen it, and so, because the other guys would have seen it if they had the low temperature STM. Okay, sorry.
No. I mean, go ahead. That's the
Mike,
point of, and also, you had a question, Tyler?
Oh, I was just wondering if, Mike, if you wouldn't mind mentioning how this has kind of led to QPI, which is such a big thing now, right? Like, do you have any sort of I don't know, things you could mention about historically how that came about?
Oh yeah, well, it's just kind of funny. I mean, I did not come from a surface science background, and so it was obvious. We got the dispersion by looking at the energy dependence, of the wavelength, which is what quasi-particle interference is. The quasi-particle interference gives us the ability to measure the dispersion by looking at the wavelength as a function of energy, and so we did that. We demonstrated that in this paper. But then the funny thing is, I went and gave a talk at wherever Ward Plummer is, Kentucky, Oak Ridge, yeah. Oh, sorry, yeah, Oak Ridge, where he was, not now. And he's a big photo emission guy, and so he was saying, Mike, did you ever think of doing the Fourier transform, of the surface and getting, like the Fermi surface? And I was like, well, why would I do that? I can just see the waves. I could just measure the wavelength from the picture, And he was like, no, and he was trying to explain to me, Fourier space. And I know what Fourier space is, but, I just didn't understand it really in the context of surface science. And he was like, everything happens in Fourier space, because he's a photo emission guy. And so I think Ward Plummer is really the first to do the Fourier transform, approach, where you just take an image of the surface, do a Fourier transform, and get the Fermi surface. That was Ward Plummer. I think his group was the first to do that. It was just kind of funny. It's just, because I didn't even think of taking a Fourier transform, because I was like, well, I can just take a ruler and measure the wavelength. Why do I need to Fourier transform it?
But this was the first experiment looking at surface waves of electrons, right?
Yeah, this was yeah, and we totally measured the dispersion, and yes, that's correct. But I do want to give some credit also to Faden Navoris, who around the same time as this, there is another group who also should share some credit. Faden Navoris and Yukio Hasegawa, who is now an STM guy in Japan, who's a really good guy. And he was Faden Navoris's postdoc, and they were doing experiments on gold at room temperature. And they did see these waves by taking very careful, like for them, like they would take an image of the surface and you couldn't see any waves, but then because it's room temperature, but then they did these very careful DIDV maps, and they were able to extract some of this wave stuff. So I would say that we did this and they did the gold work at about the same time. So I can't say that this was, the very, I would have to share that credit with Faden Navoris.
Nice. And then I'm curious, you brought up kind of the how this kind of at IBM, you implemented this that kind of low temperature STM. I'm curious, if during the experimental process, how difficult was that to get it set up for the first time and get that process
yeah,
initiated?
Let me explain. First, I just want to say Don Eigler invented the technique, and I was Don Eigler's postdoc. So Don Eigler is the person who developed that, and Don Eigler, who's still alive, he's retired now, but he's a genius at instrumentation, and he's a great physicist too, but a particular genius at instrumentation. And he developed, it was very difficult to develop this ultra high vacuum, low temperature STM for various reasons. Now the problems are all solved. It seems really easy, but at the time it was really fucking hard, because you had vibration isolation, sample transfer, all the stuff. And it was a really difficult challenge. And he is the one who solved all those problems. And it took him a hell of a long time. He was a postdoc at Bell Labs.
Okay.
And he was working for years trying to develop it. And then he kind of almost got it to work after many, 4 years or several years working at Bell Labs. Then he was hired at IBM Almaden, and they just gave him free rein. And then he had to work for another 5 years, just working solidly, developing this instrumentation. And it's really to the credit of IBM that they supported him. You know, he didn't have any results. He was just this crazy guy working in the laboratory, building all this weird machines that nobody quite understood. And then, you know, one day he was suddenly moving atoms. He was like, look, it works and I can move atoms. And everyone was like, oh my God. But, you know, I really want to credit Don Eigler, his genius and his hard work, because he just worked single-mindedly going after this load. Because as soon as Binnig and Rohr invented the STM, Don Eigler realized immediately that, oh my God, this thing's going to work, you know, 100 times better at liquid helium temperature. And he happened to have done previously some ultra high vacuum work at liquid helium temperature, not with STM, but using some other weird technique I can't remember. And so he immediately saw that if he could get this STM to work at liquid helium, then it would be just amazingly great. And he was right, but he spent, you know, many years developing that technique, and it was really extraordinary.
Yeah, thank you. You know, that's amazing. Speaking of kind of the moving atoms around, I kind of wanted to then move into the second of these, you know, two papers, which I think kind of go hand in hand. And so this is the confinement or the corrals. So we move from the stadiums now to corrals, and in this case, this paper is talking about the kind of placing with the STM. Placing 48 iron atoms on this copper surface in this kind of spherical shape around like what I think it's a 71 angstroms in radius, and you know, confining those surface state electrons in that kind of a tight sphere is creating these really beautiful standing waves. So it's kind of taking the standing waves that, you know, we saw in that first paper and looking at now, confining them and engineering these beautiful nanostructures. So like we can see in figure, you know, 1A and 2, we're seeing this kind of, you know, beautiful structure with these standing waves that are interfering and making this great pattern. And in the interest of time, I guess I won't dive too deeply into this. This was kind of some of the stuff that fascinated me a lot, was looking at kind of these DIDV measurements and over the open terrace, the center, and 9 angstroms off, and how you really started to see then the kind of, you know, zero angular momentum states at the center, and these new states that are dominated by this kind of these new angular momentum states start arising as you kind of go off center, and they correspond, you know, really interestingly with the theory. And I also, I mean, I guess briefly. I was just, you know, curious about the whole, like, you said that there was this complication with the like minute required for taking the measurement, and how, like you said, what is it, roughly 20% of the border atoms would kind of move during that time. I was wondering, how did you first like kind of see that, and what kind of complications did that put into the getting the results? And then again, if anybody else has any other questions, feel free to jump in. But I was just curious about that specifically.
You mean the movement of the atoms?
Yeah. So maybe if you could explain that a little bit. I know. Yeah.
It's just funny because I totally don't remember that. That's so fast forward to the details. I just totally don't remember. But I do remember that we sometimes could make the atoms move, you know, with the current from the STM tip. But the degree to which that affected these measurements, I don't remember that too well. I don't think it was a huge big problem for us. But I do remember that was a phenomena that I thought at the time was very interesting, and I was, you know, and that actually got me interested in electromigration, you know, and this idea of like, wow, what is the current actually doing on the surface, and how is it interacting with surface objects and pushing them, and, you know, what is the mechanism of electromigration, you know, which is the movement of small objects under the influence of an electrical current. And that's something I'm still working on. I'm actually working on that even today using, you know, graphene. But at the time, you know, we never were able to delve too deeply in that. And I know that, you know, under some circumstances, we were able to take really nice data without the atoms moving too much. So I don't think that was really one of the big problems. I think for us, the bigger problem was this idea that we really wanted sharper line widths. You know, look at these line widths, you know, they're pretty broad. And we were really hoping, and that's because of the confinement, you know, the electrons can't stay confined for very long, and the electrons you know, if the electrons were really confined, you know, those would be very sharp peaks, but instead we get these pretty broad peaks. They definitely are showing this particle in a box behavior very clearly, very nicely. And I think that's kind of extraordinary because after some, you know, some significant analysis that really was performed by Eric Heller of Harvard, he, you know, we realized that the electrons really, if you can sort of think of it, you know, in this way, they're only really doing like one bounce, you know, like they're just moving and they're like bouncing, just one traversal of the object before the electrons, you know, they go across the object, bounce, come back, and then boom, they're gone, you know, so just, you know, one bounce and interfering with themselves. They're not really bouncing multiple times, they're escaping because the surface state is so strongly coupled to the bulk three-dimensional electrons. And so that was kind of the bummer for us because we wanted to be able to see more complex interference phenomena such as chaotic behavior, which we were unable to do because of this problem of the leakiness of the structure. And so that I think was sort of, you know, when I think back of this and what we wanted to do, what we were able to do and not able to do, the real problem was the leakiness, you know. And at the time it was kind of interesting. Oh, why is it so leaky? You know, because we would make the wall twice as thick, you know, and we thought, okay, if we make the wall twice as thick, twice as many atoms, we should get a narrower line width. But it did not narrow up. And so it's very frustrating. We were like making all these really thick walls for our structures and the line width just stayed broad. And then Eric Heller, you know, with the help of Eric Heller, we realized that what was happening is that the atoms themselves were coupling because the two-dimensional surface state electrons are orthogonal to the bulk states. They don't couple to the bulk states, but when you put the atom there, that couples them to the bulk. So you know, the naive picture is that the electron is going, it's hitting one of the boundary atoms, and then it's reflecting into the bulk. So no matter how thick we make the walls, we can't really increase the lifetime, unfortunately.
So, Mike, I think that may actually brings kind of interesting modern experiments into complete 2D versions, right? Say, if you just do similar thing in the graphene or something like the 2D system, you may actually you don't have to worry about this leakiness to the bulk state anymore, right? Have you considered doing those kind of experiments into 2D?
Well, there's this guy named Philip Kim who realized that there's this Klein tunneling in graphene, right? You know, that completely screws it up. Okay, so the but it's the bilayer, right? If you have a bilayer, then you're good, right? Yeah. And so yes, we definitely have been thinking about that. And I would say, you know, to be quite honest, the person who has done the best job of exploring that is Jairo Velasco, who's now at Santa Cruz. And he has recently been publishing some papers where he is making these little stadiums, quantum dots, you know, and he's doing it with bilayers. You know, I think he did some work with the monolayers, but with monolayers of graphene, you get the Klein tunneling. So again, you have the problem of leakiness because of the stupid, you know, not stupid, I'm sorry, it's because of Klein tunneling, you know, and then, but in the bilayer, Jairo was able to show you get a lot stronger confinement. So Jairo has been able to see some interesting behavior, which is starting, he hasn't really demonstrated scarring of the wave function, I don't think, I really convincingly, but he has started to see some interesting behavior, which is starting to show signs that should lead, you know, to the observance of quantum chaos, I think. So he's really been pushing that, and that's been pretty cool. And I just want to say the person who really came up with that idea too of using this technique to look at quantum chaos is Mark Sherwin. Because when I was doing this work, it was Mark Sherwin who said, Mike, you should make a stadium. And I was like, why? What's the big deal about a stadium? And it was Mark Sherwin who really understood all that.
Very interesting. That's cool. Well, I'm going to then cede my time over to the next presenter. So here's, again, the kind of cover photo for the presentation was that corral picture. So very, very interesting stuff. But I'm going to now turn it over to Haiyue, who will talk about the next paper.
Hi, I'm Haiyue Huang here. And the paper I'm going to introduce today is about the pseudomagnetic fields in graphene nanoribbons. Next slide, please. So before I really jump into this paper, I want to give a little bit of background information about the real magnetic field. Instead of the pseudomagnetic field. So for real magnetic field, it will induce the Landau levels. And if you put a graphene sheet in perpendicular magnetic field, you will have those Landau levels corresponding to the cyclotron orbits of the electron in graphene. So instead of seeing a very continuous density of states, if we turn on the magnetic field, we are expected to see some bumpy density of states and several peaks. Next slide, please. So we are trying to make an analogy here by using string as something called pseudo-magnetic field. So it's not a real magnetic field, but it can generate similar effects as the real magnetic field. So in a previous publication by Professor Andrea Geim, they discussed that if you apply string to graphene, you actually bring the gauge field to the material. But if the string is just uniform, say a simple example here is that if it is uniaxial, then you are not generating an overall pseudomagnetic field effects. The result you will get is just a little bit shifting of the Dirac position, a little bit off from the Brownian zone, but the band structure of the graphene is not really changed. So in this paper in 2010, they discussed that if you really want to have a strong and uniform pseudomagnetic field, what you really need to do is to deform the graphene in a very weird way, showing this figure here, that you have to apply kind of stretching along the 3 directions, angled 120 degrees, and you will have to compress it a little bit along the other 3 directions. So in that paper, although they theoretically predicted the strong pseudomagnetic field effects, they also say that it is difficult to achieve experimentally. And next slide, please. But in the paper we are talking about today, Dr. Crommie did it very successfully and see it experimentally and graphene nano bubbles. So those bubbles are formed after synthesize and during cooling because of the different thermal expansion coefficients between graphene and the platinum surface. So the first good sign we see is from the STS spectra. It's an indication of local density of states, and we see that for the black curve compared to the blue curve, there are several extra peaks compared to the flat graphene. And this is an indication that we could probably, what we see here is probably due to the pseudomagnetic field. I put a graph here, which comes from the Andrea Geim's paper, that they theoretically predicted that there will be several extra peaks in density of states if you apply the string along the direction by the red arrows here. Next slide, please. So this is a good indication. And then if we want to further support this hypothesis, and we look at the we can look closer at each of the curve. So what they did here is that for each of the STS spectra, first identify the location of the peak on this curve, and then index each of the peak. And then we try to see if the energy of each of the peak and the index follows this line. So if this follows this expression here, the square root of n should be linear proportional to the energy. So this is a lot of data collected on different positions on one nano bubbles, and together from 5 different nano bubbles. And we see that the linear relationship is very reasonable. So this is consistent with the hypothesis of a strong pseudomagnetic field. And we can further extract information about how strong this pseudomagnetic field is by calculating the slope of this line. Next, please. And on the previous slide, it is the collective data from 5 different nanoribbons. Now we'll just look at single nano bubble, and then we see that for each as we go along this red arrow, we can monitor its height, and at the same time, we can get the magnitude. We can get the strength of the magnetic field by fitting it into a linear, as we did in the previous slide. And then we can plot them in the same graph as shown in figure A. We can also do the same thing in theory by simulate the triangular shape using using continuum elastic theory. So we see that this shape is triangular, approximately triangular symmetric. So this is probably one of the reasons that we can observe this strong pseudomagnetic field. And the other information that's given by this plot is that the pseudomagnetic field is relatively uniform as we approach the peak of this nanobubble. And from theory, we can see that the results is very similar to what we observed in experiments. And altogether, this is a very strong evidence that in a nano bubble that which the shape of which is approximately triangular symmetric, we can indeed observe this strong pseudomagnetic field effects. Yeah, that's all about the paper, and I have some questions that out of my own curiosity, because I know there was a theoretical paper, but I'm wondering if this phenomenon was done like by intentionally searching a triangular shaped graphing structure, or it was kind of by accident.
What do you think?
I think it's like something in between, that you have this in mind.
No, it wasn't in between. It was totally by accident. And it's just the funniest thing because it's just really the funniest thing. I mean, because Antonio Castronedo, who I think is on that paper, was he on that original paper with Geimer? Maybe not. I can't remember the theory paper. Antonio Castronedo?
Jack, could you go to previous?
That the paper with Geim where they predict, well, it was Francisco Guinea who is on that paper, I think. Yeah, let me see. Okay, it's Guinea, Katznelson, and Geim. Okay. Yeah, okay. So, so Antonio Castronedo is a theorist, a solid state theorist who's really into graphene, and he's good friends with Francisco Guinea, who people call Paco Guinea. And so Antonio Castronedo was really into this effect. This is something that was very interesting to Castronedo at the time, because he wrote that big paper on graphene. He was really into graphene at the time. And he was doing a sabbatical at UC Berkeley. And we just happened to be growing graphene on platinum for some other reason that, to be quite honest, I can't even remember why we were doing it, but we were growing, for some reason, we were growing graphene on platinum. And when you grow graphene on platinum, the growth you do at very hot temperatures. And so you grow the film at hot temperatures, but then as it cools down, everything just kind of, shrinks. And so then, you get strain and, differential thermal contraction. So you get these weird bubbles and stuff. And so my students happened to be doing spectroscopy on the graphene, trying to see what's the electronic structure, and they did the bubbles, and they were seeing these weird peaks in the spectroscopy on the bubbles. And Antonio Castronedo just happened to be doing sabbatical at Berkeley, and he was in my office, and me and Antonio were just talking, we were just chatting about whatever. And then my student came in and they were saying, Mike, look at this weird, keep seeing these weird peaks, in the data. Every time we go on one of these bubbles, we see these weird peaks. And I was like, wow, okay, maybe it's a quantum confinement effect. I don't know. I had no idea what it was. But then Castronedo just happened to be in my office, and he was like, Mike, I think that this is the pseudomagnetic field. And I was like, what pseudomagnetic field? I was like, what are you talking about? And then Antonio Castronedo said, Mike, you should really check, he basically, pointed us in the right direction. And so, I mean, it was just completely fortuitous. So it's just the funniest damn thing. And then, he sort of helped us out a lot in understanding what's going on. And then Francisco Guinea, got involved, and they did the continuum modeling of the strain to really, to sort of see if the numbers could actually work out. And they did quite nicely. I will have to admit, like, there's something about this project which there was a certain disappointment for me, just our lack of ability to control, these bubbles. Because after this result, I was so excited about this topic that we spent 2 years trying to, control the bubbles, or like figure out how to control the strain using different techniques, and we just totally failed, and so that I always have a little bit of, it turns out that to control the strain is really hard in the graphene. Others have done a better job, as I think you show on that next slide. But in my group, we were trying crazy things like putting, a polymer. One of the ideas I was trying was to make polymers of azobenzene molecules, molecules that would change when you shine light. And so my great idea was, if I could put the graphene on top of the polymer and then shine light, I could make, control the strain as the polymer expands. And we spent like 2 years trying to do that, and just completely, totally failed. But this is the best we were ever able to do, which is just by accident. Oh well. So the point is, it's better to be lucky than
Yeah, Mike, a quick question. So do you think this is special for graphene, or other 2D materials which form such bubbles would do the same thing?
Well, I mean, other materials should do the same thing. And in fact, Paco Guinea has papers, and I think other people as well, that I think similar things should even happen in the TMDs. I think it's it's the question of whether or not these, I've forgotten all the theoretical details, but I think, something about this honeycomb type symmetry, and, and as you change, the strain changes the hopping amplitude for an electron to hop, from one atom to the next, and there's just this funny quantum mechanical new detail that it sort of behaves just like a vector potential, as you do the strain. And if you go through the math, if you strain certain TMDs, like the 1H TMDs, then you should get the same thing, and so I'd say it's it depends on the symmetry of the two-dimensional material and strain, but you should get it. And so, yeah, absolutely. Other 2D materials should show it, but they have to have a certain structure. I know that the honeycomb structure shows it quite nicely. I don't know about other structures. Maybe they might show it also, but definitely systems that have this kind of honeycomb type structure in 2 dimensions should show it, not just graphene.
Thanks.
Yeah, I have
Right.
another question. That's there's a whole field about string engineering of 2D materials now, and they're trying to deposit the 2D materials on all kinds of patterned surface, like those trench and those tents here. Do you think we could maybe generate the similar phenomenon in a more controlled way nowadays?
Oh
By just-
yeah, I do. I mean, my group, I tried for 2 years and failed, but other people, have better ideas, for how to do it. And absolutely, I think it's just a question of, enough people. It's a hard problem, how to control the strain, but there's a lot of really smart people out there, and and especially with people's ability to do micro machining, and so you could take like silicon, micro machining of silicon structures that you can then move, via various electrical engineering tricks, and then combine that with the 2D materials. And oh yeah, I strongly believe that eventually people will be able to manipulate the strain in these small structures, with great precision. It's just a question of time. I mean, they're already showing, lots of progress over the last 10, 15 years.
Great. Well, I think we might have time for more questions at the end, but I'm going to move us on to the next presenter. So I will put up those slides.
So, hi, I'm Ashwini. So I'm working with Dr. Jeremy Levy at the University of Pittsburgh. So today I'm going to talk about the paper, which is about the 8 states of chiral graphene nanoribbon. So in this paper, the STM and STS have been used to examine the electronic structure of graphene nanoribbon, how the electronic structure of graphene nanoribbon depends on the chirality of GNR edges. And also, so the STS measurements reveal the presence of one-dimensional GNR edge states. Next slide, please. So the chiral graphene nanoribbons have both zigzag and armchair segments at their edge. So we can define a chiral vector, so which specifies the number of carbon atoms in both zigzag and armchair segments, and the angle between them is the chiral angle. So it exhibits like very interesting features like tunable energy gaps and also the presence of one-dimensional edge states with unusual magnetic structures. So in the figure B, we can see the topography of a monolayer GNR at the room temperature. So it's straight atomically, it has straight atomically smooth edges, and the line scan will give us the GNR height. And another interesting feature we can see in the figure is the bright stripe running along each edge. So it marks a region of curvature near the edge, and it's similar to the curved edge structures observed in graphite step edges. And so in the paper, they have also mentioned they ruled out the possibilities of collapsed nanotubes and folded graphene boundaries. So in the figure C is the low temperature STM image, which shows finer structure in both the interior GNR terrace and the edge region. Next slide, please. So here we can see a clearly atomically resolved topography image of the terminal edge, and it's a 8-1 chiral GNR. So such high resolution images can help us experimentally determine the chirality, and we can eventually create such structural models as shown in figure B. So near the edge in the topography image, we can see rows of protrusions. So by comparing this row to the terminal edge of the GNR, we can find the chiral angle, and they found it to be 5.8 degrees. And then to probe the electronic structure, they have done scanning tunneling spectroscopy. They have done the STS in both direction, perpendicular to the edge and parallel to the edge. So as we can see, there is a change in the edge spectra in both directions. So there is a broad gap-like feature having an energy width of approximately 130 MeV. But the dominant interesting feature is the two peaks that arise within the elastic tunneling region close to the edge. They are asymmetric in intensity, and it's also not centered around 0 voltage. And their intensity grows as we move to the edge. And as you can see in the figure D, the spectra changes. Spectra also changes in the direction parallel to the edge. Next slide, please. So they have, from the previous STS data, they have done some Lorentzian fits and find the edge state peaks, so, and then plotted the spatial dependence. So in the direction perpendicular to the GNR edge, the spatial dependence shows an exponential behavior, and whereas in the direction perpendicular to the GNR edge, it oscillates with an amplitude of approximately 20 angstrom, which is close to the 21 angstrom periodicity of 8-1 chiral GNR. And from this oscillation seems to arise from the kinks in the zigzag edges. And in the figure C is the gap dependence with the width for different GNRs with different chirality, and they found a clear inverse correlation with GNR width. So the spectroscopic features correspond closely to the spatial and energy dependence predictor for one-dimensional spin polarized edge states coupled across the width of a chiral GNR. And next slide, please. Next slide, please.
Yeah, I'm just curious. Tyler, you had a question. I wanted to just pause.
Yeah, maybe it would just be a quick one. So we were talking in the beginning about these standing waves, and there was a paper from Pascal for the 7A GNRs where they looked at an oscillation of the DIDV density along the ribbon, sort of close to an end, and use the Fourier transform of that, then to try to get the one-dimensional band structure out. And so I wondered how we should think about these oscillations. Is it more to do with the structure of the ribbon, or if it's close to the edge, can you get like a dispersion out of it as well, or?
Okay, yeah, let me think about that. I don't think that you really can get the dispersion for this, because if I think that this is more like the flat band. This is more like the zigzag flat band, you know,
Okay.
whereas in the 7A GNR, that's a dispersing band, you know, that they're looking at. And so here, what was really interesting was to look at the magnetism of the chiral edge. And so, you know, from a band structure perspective, I think, you know, it's a very flat band. And so we're just, you know, kind of looking at, so I guess here we're kind of looking at, I guess I would say more like, you know, the one-dimensional flat band characteristics.
Okay,
Yeah, so we couldn't really get that dispersion.
thanks.
You know, we wanted to see evidence of magnetism. That was really, you know, and so to see the splitting, it's basically the splitting of the flat band. I think, if I'm remembering correctly, you know, that was kind of the interesting thing about this paper.
So to compare the experimental data, they have done some theoretical calculation based on this Hubbard model Hamiltonian. So they have done calculation for two cases. For first one, when U is equal to 0, which means there is no electron-electron interactions giving rise to magnetic correlations. And then when U is equal to 0.5 times T, where T is the Hoping integral. Next slide, please. So here in the band structure, the blue curves represent the U is equal to 0 case. As we can see, when at 0 energy, it's just a flat band, and that's not what we observed experimentally. And the red curves is for the calculations when U is equal to 0.5 times D, and we can see the splitting of the single band at E is equal to 0 for U is equal to 0 case when. So that is what we observed experimentally, the splitting of peaks. So that provide evidence for the formation of spin polarized edge states. And this edge state is just not a local effect, but it depends on the full GNR electronic structure, including the interaction between the edges. Yeah, that's the paper.
Yeah, maybe I'll just comment on something about this paper. I mean, this paper is another sort of, you know, kind of funny, lucky, accidental thing. I mean, because I know when graphene was first discovered so many years ago, and one of the things that was so super interesting to me was the edge. You know, I mean, as an STM guy, I was like, oh, I want to look at the edge. You know, how do I get the edge? And then, you know, like the guys like Philip Kim, who was, you know, in the pioneers of graphene, you know, they were making nanoribbons with photolithography, but the edges were very rough. And so that kind of made it very difficult to test certain predictions. So we were like, is it, you know, really, we wanted to get nice edges, but we couldn't. And we spent like years looking at different systems, and we never could get nice edges. And we were trying to look at chemically exfoliated nanoribbons, and it was all just garbage. We spent years looking at different systems. There was always garbage. We never got a good edge. But then finally, Hongji Dai, he did this unzipping, this chemical unzipping of the nanoribbons, and we dropped them onto the gold from solution phase, and it was just like a miracle. You know, we got these beautiful nanoribbons, and it just surprised the hell out of us. You know, it's the first time that we had ever seen a nice edge, you know, and so that was really exciting. And so we did this physics, and, you know, I was really excited about this. And you know, this paper, you know, we did this paper, which I think is really nice. And, you know, the physics is really, really lovely. But then the problem is that as we tried to go further with this, the problem is that we could not control the chirality, you know, with because these edges, these nanoribbons are coming from nanotubes, and you cannot control the width and chirality of the nanotube. So as we made more samples trying to go further with this physics, there was just so much heterogeneity in the nanoribbons that came out of this that it was really hard, you know, it was just really hard to do really careful reproducible work, because every nanoribbon was, you know, they were all different from each other, just really hard to kind of go further. And then at about the same time, you know, just because of the lack of control of the starting material, the nanotubes, you know, but then the funny thing is that it's about the same time that we did this work, this was the same time that Roman Fasel and his collaborators came up with this completely different way to make nanoribbons, which is by taking molecular precursors, which of course you guys all know about, I think, and then to link them together and self-assemble the nanoribbons. And so now I think it's pretty clear, that everyone, understands that that is a much better way to make the nanoribbons, because because the problem that we had with this work is just is getting the same type, of edges, and the same electronic structure. But with the chemical self-assembly technique, then you can really get nanoribbons that are all the same. And so after a few years, it became pretty clear that the molecular self-assembly technique is a much better way to go. At least that's how people believe nowadays. And so we abandoned this technique because it allowed us to get at this really nice edge physics, but it was kind of sort of a dead end in the sense that we couldn't control it well enough. And so now we abandoned this technique, and we sort of started using the same technique that was just invented by Roman Fasel and Klaus Mühlen, which now allows people to make these kinds of structures, these same kinds of edge structures, but with perfect reproducibility, because the molecular starting material is all the same. So this is kind of funny. So this paper is kind of a funny little relic of the past, because this is kind of showing, the farthest that we could go without molecular self-assembly, but then it's like a dead end. To go further, you need to use the molecular self-assembly, which is what we do now. And, Alex Sinitsky, for example, is a master of the self-assembly technique. Okay, that's all I wanted to say.
No, that's great. I'm going to open it up if anybody else has any other questions about this paper, this kind of work.
I have one quick question.
Yeah.
So I always wonder the naming of the chiral GNR. So is the chirality actually originated from the carbon nanotube, right? It's not the GNR that's really chiral.
I have to admit, this has always confused me too. Like, where's the chirality? I know that, it all started with nanotubes, because nanotubes were already quite mature before this nanoribbon stuff. And, but when maybe, I don't know, maybe Philip Kim could answer this question better. But I know that people sort of adopted a very similar terminology for the nanoribbons, but what is actually, why do they call it chiral?
I think that it is probably more of the historical remark, as Mike said. It's coming from the nanotubes, and originally there are people just think that there's the achiral nanotube, chiral nanotube. Achiral nanotube is armchair nanotube, for example, or that completely zigzag nanotube, something like that, say 90 or something like this, is often called the achiral nanotube. And chiral nanotube is anything in between. I think that was a historical term. I don't think it has a kind of really deeper meaning. When you identify the nanotube structures, you need the two indices that using here, then 8-1 or something like this. And what people want simply just to distinguish between some specific directions. Armchair and zigzag direction is some specific called achiral. Anything between is chiral. I don't think that's a modern term of the chirality is rather different in that regard. So should not worry about too much about this terminologies.
That's great. Thank you. Any other questions? Okay, go ahead.
Yeah, quickly comment on this. I think that the idea of a chirality here comes from the fact that those chiral ribbons don't have a vertical mirror plane. So like, a straight zigzag or a straight armchair ribbon, it has like a vertical mirror plane which goes along the direction of the GNR, right? And when it's chiral, then indeed, this plane doesn't work anymore. So you can kind of think of a right hand and left hand versions of this ribbon, which basically what chirality is. So, I mean, from this point of view, I think it's a valid definition.
Okay. Yeah, that's interesting. Thank you. Okay, any other questions before we move on to the last paper in our lineup? Cool. Well, I think that's a great time then to move to the next paper. which is inducing metallicity in graphene nanoribbons. And I'll let.
Hi, everyone. It's Mamun Sarkar. I'm a postdoctoral researcher at Dr. Sinusis lab at University of Nebraska-Lincoln. I'll talk about the like this paper where the metallicity was this concept was bring to the graphene nanoribbon community by introducing like symmetric superlatives at 0 mode. Next slide, please. So the concept used in this paper was based on the 90s theorem from Professor Elliot H. Lieb, known as Lieb's theorem, and also like some additional work later came in 2010 from the missing carbon atom of graphene. So basically in this theory, what was important is the like, if you consider graphene and there's like two kind of sublattice of depending on the connection. So if you see this example of the graphenic structure, so red is one type of sublattice and blue is another type of sublattice. So if there's a like imbalance, if the total count of the blue and red, and then the imbalance, the surplus of the carbon atoms, eigenenergy is located at the E equal to 0, which create the 0 modes. And this 0 modes energy dispersion is can be like well calculated in the FSH model using these equations where T1, T2 is depending on the like hopping parameter in the like sublattice sublattice mode, 0 mode. So if there is the sublattice imbalance equal to 2, meaning like if you consider the red and blue, if you count both, for this, for example, for these ones, the red is 48 carbon atom and blue one is 46 carbon atom, which give us 2 imbalance. So there is 2 and 0 mode of carbon atoms in this unit cell. So when there's a like this 2 like imbalance is 2 and there's a like hopping parameter T1 to T2 in this mode is equal, then the total energy according to this equation is 0, meaning it behaves as a metal, which was really interesting. And if you can go to next slide. So based like there's a previous slide. Yeah. So based on this idea, they came up with the molecular precursor design with extra like methyl group, like extra carbon in the unit. And while they coupled to make polymer and polymer to GNR at 300 degrees Celsius, there's a like sublattice imbalance in the unit cell. So in one unit cell, there's a like 2 net like imbalanced superlattice or like sublattice, and there's like external. And after like when they did at 300 degrees Celsius annealing, they see this like GNR form with there's a like zigzag edge at the like armchair edge of the GNR due to the extension of the metal ring, and there's a like cove edge created due to this extra panel ring. And they used to increase the annealing temperature to 350, where there's a like new bond connected at this cove edge to make the 5-member ring, and changes the sublattice like symmetry. And it from the like a high resolution bond result STM and STM, you can see the exact structure that was predicted like in principle. And this shows point you have like 5-member form, you don't see this blob. So this blob actually white blob came from the like repulsive hydrogen at the edge of this cove region. So since there's a like carbon-carbon bond formation and really like release of hydrogen, so there's no blob here. And you can see the similar large-scale images as well. So the periodic white blobs, and for 5 SGNR, you don't see that much. Can you go to next slide, please? Yeah, and in this they showed the electronic properties of these two GNR. So before forming 5-member rings and after like forming 5-member rings. So on the left, you see when before 5-member ring formation, you see the electronic properties of this GNR. In the left side, in the middle, you see the experimental DITB plot, and the right side is the DFT calculated one. And you clearly see, since as predicted through the like structural sublattice imbalance from Lip theorems, that energy, like you'll see, zero mode created. So at 0 volt, you see a strong peak, which is like relevant to the like expected theoretical model that it creates a 0 modes due to sublattice imbalance. And when you have like higher bias and like you see the balance band mode and conduction band mode, which is totally like without this sublattice imbalance, it could be the semi-conducting GNR. And because of the sublattice, it is like totally now magnetic GNR. So if you see the bottom left corner, it's the LDOS mapping from the STM. And at the 0 mode, you see the electron density is at like look like a snake, which moving around at the edge of the sublattice imbalance of the 0 mode. So it's like nice shining pattern. And when you have like higher voltage at 1.3 electron volt biasing, then you can see the electron density is usually on the edge of the armchair region, which is like seen previously for this armchair kind of event. And from next right in the middle, you see the theoretical calculation, which exactly matched with the experimental results. Similarly, for when you change, do this similar kind of measurement for 5S GNR, meaning when it created 5-member ring, and you see there's a like splitting of the 0 mode. So 0 mode is there's no longer a strong peak at 0 mode, but you see it split up. And electron density at the bottom, you can see it's not like as bright as the like before forming, but it followed the same pattern of the snake-like go through along the axis of GNR. And similarly, the theoretical calculation shows the like splitting of the 0 mode due to the formation of new bond, like a carbon-carbon bond at like 5-member ring. So if you go to next slide. And this was like confirmed by the theoretical calculation. So at the top left, you can see the calculation for the like sawtooth GNR or like SGNR before forming the 5-member rings. And you can see at 0 energy, the band is split between like Fermi energy and like there's a like very small gap, almost 0. So there is like metallic behavior. And at the bottom left, you can see for similar calculation for 5S, and there's a like the 0 mode, like the band is dispersed in between the Fermi level in the conduction band and the valence band, which is the common for the metallic behavior of like GNR. Like any metal has like band is dispersed in conduction band and electron or like valence band. So and further, they also like check the robustness of this metallicity by inducing calculation by spin polarized calculation, considering the spin polarized DFT calculation. So if you see the top right, that is calculated for the like before forming 5-member rings, and the bottom right you see after forming the 5-member rings. So what is important here is that when you do the spin polarized calculation, you can see there's a like gap opening at the like 0 mode. And when you consider there's a like effect of the doping and the substrate. So it was, if you see the top right corner, so there's like when you do the calculation considering this doping and substrate, so this gap state is disappeared. So which means there's like a ferromagnetic transition in this GNR. So it's like logically you can say the metallic GNR. But if you see the bottom right corner, So there is no effect on the doping or the substrate. So like there's no change in the like states of the band state in spin polarized calculation. So which is which you can probably guess that the bottom GNR is more robust than the like top one. So the reason is like the change of the structural differences between these two GNR. If you go to next slide. So they explained the reason for this variation of electronic properties between these two GNRs based on these calculations. So it depends, like there's a like parameter they use, like the hopping parameter. So when if you consider the graphene lattice with nearest neighbor and second nearest neighbor, the effective hopping when you do for before forming the 5-member ring GNR, if you see the top left, like bottom left corner, so you see the hopping parameter is almost proportional to the second nearest neighbor, because the electron state density state is localized at the alternating like similar sublattice. So there's a like gap between the density. There's like one neighbor gap. So this is like second nearest neighbor. And if you see the like the left bottom left image for 5s GNR, it is like disrupted when it forms 5-member rings. The bipetal lattice is symmetry is broken due to the carbon-carbon bond formation, and the hopping parameter is now almost proportional to the nearest neighbor, not the second nearest neighbor. So which creates actually, so due to this 5-member ring formation, it changes the structural parameter and also the electronic properties, which is also further can be noticed in further if you see the right side images where calculation is done on the isolated like 0 mode GNR, SGNR, and or like before forming 5-member ring and after 5-member ring GNRs, and you can clearly see the polarization difference between these two GNR. So actually, like this is really interesting and like nice way to like think in chemical design. And like my question with to Mike is like, what was the thought process when you work on this GNR? Like, I mean, did you think like do the theoretical calculation first to observe this hypothesis and then do the chemical design and all the measurements, or what was like that?
Okay, yeah. I really this is this is one of my favorite papers. I mean, it goes way back. I mean, you know, because Chagan Bhattar, you know, really who is a program manager, you know, who really helped fund this field and make all this bottom-up nanoribbon stuff. He fostered it by funding, you know, different groups to explore this, and Chagan would force us every year to have like a big conference, and everybody would come and talk about nanoribbons, and it was really a lot of fun. And many of the people in the audience, I think, went to these things. And Roman Fazl, who's kind of, you know, the father of, you know, Roman Fazl and Klaus Mühlen, you know, the father of this bottom-up nanoribbon technique. You know, I just remember at one of these conferences, I was sitting there with Roman Fazl and we were chatting, and I was just really confused. Like, can you have a metallic nanoribbon? You know, because people never talked about metallic nanoribbon. Like, you know, Stephen Louis wrote with Marvin Cohen wrote this very famous paper that armchair and zigzag nanoribbon should both be metallic, even though in at the tight binding level, zigzag nanoribbon should be metallic, but at the DFT level, they're semiconductors. And so there was a lot of people thought that you could never have a metallic nanoribbon because there would always be something would happen. It would become magnetic, or you'd have a charge density wave, or, you know, so to me, at least, I was personally very confused. Like, can you have a metallic nanoribbon? even in principle. And I thought I was like really dumb for not knowing the answer. But then I was talking to Roman Fossil and I said, Roman, I don't really understand. Can you have a metallic nanoribbon? And Roman, thought about it. He said, Mike, I don't know, And so it was like we were both just super confused. And then all this topological stuff, came to be. And then it became very clear that if you could just have these zero modes equally spaced, with perfect symmetry to the left and to the right, it should be metallic. The gap should close up. But even if the gap closes up, you might ask, okay, well, could there be some other transition, structural transition, or some other physics that will interaction-based physics that will open up a gap? And so we really very much wanted to make a nanoribbon that had this symmetric electronic structure, meaning these zero modes that look the same as you move to the left and to the right with this perfect hopping symmetry. And so that was our goal, was to make a nanoribbon that had that symmetry. And so one day we realized that this, we call this the sawtooth nanoribbon because it looks like a sawtooth. And we realized, oh, the sawtooth should have the symmetry. And so, we went about, making this sawtooth, in collaboration with Felix Fischer. And so that was sort of our thought process, okay, was to, make a ribbon that had this symmetric zero mode structure, and this sawtooth could give it to you. Of course, it's there's issues, because it's not, it's non-regio regular, so we have some real serious issues with this nanoribbon. But without getting into those details, it did work. We got this this beautiful symmetric structure that then did have this sort of metallic kind of behavior. But then there was this other issue where we would see these, we would see these different types of nanoribbons, the ones with the big white bumps and the ones that were really flat. And it took us a while to kind of figure out what was going on. And that part was also quite beautiful because, we had such a narrow, flat metallic band that we eventually realized, oh my God, this is not actually metallic. It's metallic when it sits on the gold, because the gold is doping it and, reducing the electron-electron interactions. But if you take it off, you should have an insulating, it should be a metal to insulator transition because it should become a magnetic, which is actually quite interesting, but, it's sort of not a good metal. But then this really funny thing, where is it? It's in this, in the, like this, is it here? If is it here in this picture, like, you close up the little chemical bond. I don't know. Oh yeah. On the maybe the lower right-hand side, you can see that the little chemical bond is closed up. Basically, the zero modes are sublattice polarized. And because of the which you sort of described, because of this sublattice polarization, you get a very narrow band because you can only get second nearest neighbor hopping. And so these perfect, zero modes are sublattice polarized. And that means that typically you can only get second nearest neighbor hopping because you can't go to the next neighbor because there's no wave function amplitude on the nearest neighbor for a bipartite lattice. And that's kind of a problem because that means that your metals are always going to be very shitty because they're going to be very narrow band. But then if you break the sublattice symmetry, if you break the bipartite symmetry by causing the same sublattice to bond together, then that completely changes the electronic structure. So for me, that was actually the most interesting part of this work, is the fact that by simply doing a teeny tiny break of the sublattice symmetry, this one chemical bond, like you can see it in these images, the lower right, like you see these two on the lower right, at the far lower right. Actually, maybe I can even do it. I can do my annotating. Yeah,
good. That'd be great.
Let me draw like right here. See there? That chemical bond is not formed, but now it is. So for me, this is the most interesting part of this whole paper, is that on this one right here, where I drew an arrow, I don't know if you can see the arrow, that chemical bond is not formed. And so this one on the left has sublattice, beautiful bipartite sublattice symmetry, which means that for electrons to hop through the zero modes is really hard. You only get second nearest neighbor hopping. So you get a really shitty metal. But now if you close that one bond here, and now I draw another arrow, then you break the sublattice symmetry, and just that one chemical bond just completely changes the total electronic structure. Now the bandwidth has changed by like a factor of 20. that one bond changes the bandwidth by a factor of 20 because that one bond breaks the sublattice symmetry. So now you no longer have bipartite symmetry. And so now there's wave function amplitude on both sublattices. So now an electron can move so much easier because it can hop to the nearest neighbor instead of the next nearest neighbor. And so for me, that was really the amazing thing, because if you look at this unit cell on the left, there's like, I don't know how many atoms there are. There's like, 120 atoms or something. I don't know, maybe not that many, but on the order of 100 atoms, whereas on the, and you're just changing one chemical bond for 100 atoms in the unit cell, and you're changing the bandwidth by a factor of 20. So that's really kind of extraordinary. And so I really like that. And another thing that is really kind of cool about this is, suppose you don't break that sublattice, so that I think is kind of interesting that we can change the metallicity so dramatically with just one chemical bond. It's kind of extraordinary by breaking the sublattice symmetry. But then another thing that I really like about this is if you don't break the sublattice symmetry and you still have the narrow band nanoribbon, why don't you maybe you could go back a few slides. Let's look at the narrow band one. Even go back. Yeah, to this. No, yeah, right there. Yeah.
Okay, great.
And so now you can see this right here. So you can see this narrow band, I'm circling it, it's so narrow. And so, that's really kind of cool too, because, it's like, if you look at like, for example, if you think of, one of the exciting directions of solid state physics these days is, people talk about the moiré structure, and the more, if you can make these moiré structures with graphene and TMD materials, then you can change the lattice constant. You can get very narrow bands, and then when you put the Fermi energy into the narrow band, you get all this interesting electron-electron interaction effects. You can get a Mott insulator, or you can get something that looks like a Mott insulator, or there's all kinds of interesting behavior that can occur. And so what's interesting to me is that we should be able to get the same kind of behavior in graphene nanoribbons, because in graphene nanoribbons, we can engineer the structure to give us these very flat bands. As you can see, it's right there, a super flat band, that peaky structure at 0. And so to me, one of the most interesting things is if we could get this nanoribbon onto a substrate that allows us to gate the nanoribbon. If we could then gate the Fermi energy into that band, then I believe, it should be kind of interesting. Interesting behavior should occur. So the reason I mention this is because this is a topic that right now is of great current interest to me. Like, one of my goals is to be able to get these nanoribbons onto a substrate that we can gate. So we can gate the Fermi level into these flat bands and actually see these electron, the effects of these electron-electron interactions. And splitting and ferromagnetic transitions, and the Luttinger liquid behavior, all of this should occur. But the problem, as you guys all know, is getting these nanoribbons onto clean substrates that allow you to perform gate tunable field effect transistor measurements is very difficult. And so that's a huge challenge. That's still one of the big open challenges in this field. And so that's definitely a challenge that is one of my favorite problems, and so I'm hoping that by the time I retire, like in 10 years from now, I definitely want to, this is like one of the experiments I want to do, before
Come on, Mike, you're not going to retire.
Well, before I die or whatever, before I keel over, standing over one of my stainless steel chambers, I want to, put this nanoribbon onto a field effect transistor and gate the Fermi level into that flat band, either me or someone else. If I don't do it, maybe, Alex Sinitsky will do it, or Tyler Cocker, or Jeremy Levy. I don't know. Someone's going to do it, or Philip Kim. We got to get these stupid nanoribbons onto a clean substrate, make it clean, and gate the Fermi level into these, flat bands. I just think that would be really fun and interesting, and I would love to do that. So that's one of my big goals.
Mike, could I ask you a question related to that? So in the picture here, the DIDV, you've got that peak really looks to be at 0. And so, if I'm thinking about like molecules or something, you put a molecule on a surface, and I think of the HOMO and LUMO position, like moving around relative to the Fermi level based on what the work function of the substrate is, right? So kind of, okay, it could be here, it could be here. Yet this guy is right in the middle already. So then I wondered, like, okay, it's somehow coupled to the substrate, I guess, that forces it to be at 0. And so would it work to gate it? Like if you put it on something else, would that peak just move to wherever the Fermi level is of the new substrate, or?
No, I think it would gate. I mean, I guess the question is, when you okay, maybe that's a subtle question. I mean, like we have been, in my mind, when you ask a question, this question like you're asking, the way I think about it in my own mind is, is the electronic structure, can you think of it sort of, as a single particle electronic structure, or on the other hand, is the electronic structure purely due to some complicated electron-electron interaction? And the example in my mind would be, say, a Mott insulator. Like I have silicon, which is a regular insulator, and I can just gate silicon very normally. But if I then have a Mott insulator, and you talk about gating, when you gate a semiconductor, you're moving the Fermi energy smoothly through either the conduction band edge as you go up or the valence band edge as you go down, and you can do this very smooth gating. But then when you talk about gating a Mott insulator, where the electronic structure is due to electron-electron interactions, then this concept of sweeping the Fermi level through the band edges becomes very confusing and complicated, and maybe not a correct picture. And I think that's sort of, related to your question, like what really happens when you gate it. And I think that is an important question. And so when I look at this peak, if this peak was purely an electron-electron interaction effect, such as a Kondo peak, okay, then yes, I would agree that, gating it becomes a very confusing question. What the hell does it mean to gate a Kondo peak, right? Suddenly everything's really confusing and weird. But on the other hand, if this peak we're looking at is purely just a band structure effect, just which we believe, that was what we said in this paper, that's our belief, is that what we're seeing here is a band structure effect, then I think gating it is, you can use sort of the simpler, more straightforward picture. If it truly is the band structure, then it only becomes a question of density of states. Like, is the capacitance of my field effect transistor great enough so that as I put a voltage on my field effect transistor, the amount of charge I'm donating to the object can push the Fermi level through that peak in the density of states.
So is there an easy way for me to understand why it's exactly at 0 if it's not a Kondo peak? So put that aside.
Yeah.
And that it's not at a different, like a non-zero bias based on where, the work function of my substrate is or something.
Well, my simple-minded way of thinking about that, the way that I would answer that just, off the top of my head is that, there would be what I believe is that you have a high density of states. And so then I would think that technically it's not exactly on 0, but that, then you have some slight shifting, but because the density of states is so high, you can get some doping, but then the Fermi energy isn't going to move too far. So I would call it Fermi level pinning. So that's because if you have a peak in the density of states, you can pin the Fermi level. So, it's sort of like a Fermi level pinning phenomena. That's what I would think. In my mind, I would think that it's close enough to the gold Fermi level already that just a little bit of charge doping, causes, then charges it up and then pins the Fermi level. But on the other hand, an alternative explanation would be that this is, say, a Kondo peak. That would be like an alternative, explanation. But in either case, I think the interesting thing, regardless of the answer to that question, the interesting thing to do is to gate it, right? Whether it's Kondo or narrowband, and to get it onto a substrate and just gate it and see, because because right now the physics of that narrow peak, I think the other one, once we close that bond and widen the band, I feel like that physics is kind of simpler and more straightforward, because then, you know, there's no question of any many body physics. But for this one on the left, I think the interesting thing to do would be to get it off of that gold substrate and, you know, onto, say, you know, a TMD substrate or a graphene substrate, and gate it, and then see what happens. That's what I would really love to do.
I think we have time for like one or two more, maybe like quick questions. So I see that we have Alex Tinsky, who has their hand up, and then.
Yeah, hey, Mike. So thanks for the great explanations. They actually clarified a lot for me. I had a couple of questions. One was about this condor peak, and I think you kind of answered it already, because in this other ribbon, which we're working on right now, we're actually currently interpreting this peak as a condor peak. At least that was my kind of, you know, like an understanding. And could you comment on whether this ribbon is like conceptually different from that like chevron-based QGNR, or essentially what we see for this ribbon should be the same for that other ribbon? Because I mean, was we are also making this like zigzag region, and we are creating an electron like, you know, like sublattice imbalance, right? And that is basically this, like, it makes this radical state in this zigzag position, which causes a Kondo effect with the gold substrate, right?
Well,
so,
I mean, but for the other ribbon that we're studying, I think that there is sort of there's no periodicity, if I remember. You know, like you know, we just see the lattice is so destroyed by all of the. I mean, I guess, you know, like in the other nanoribbon, there's no because here, if this is a narrow band, then the interpretation is that it's due to the coupling of these zero modes in some kind of a lattice structure. Whereas I think in the other nanoribbon, the lattice is broken, and so, you know, it becomes very hard to have any kind of band structure interpretation. I think, but Alex, I'm sort of forgetting the details, but I would say that you know, the answer, if, you know, if there isn't a good answer to your question, sort of lies in the details, you know, because this question of, is it a narrow band or a Kondo, you know, there's almost like a smooth transition from one to the other. And it's just a question of how, you know, how big is the relative hopping amplitude, you know, between the zero modes compared to the coupling to the substrate.
yeah, but with regard to that, like if let's say we want to differentiate between the Kondo and the like periodic like, you know, hopping and such, the fact that a single unit of this ribbon also shows the zero mode peak, isn't this an evidence that it's a Kondo peak? Because otherwise, like, you know, for a single unit, there's no periodicity, right? There's no like hopping effects and such, right?
Yes, that's true. But I guess that there's always this confusion, you know, when you have two interpretations that give exactly the same answer, it's always ambiguous. You know what I'm saying? It's always ambiguous. And then you have to do another experiment, you know, like strong magnetic field, or actually, you know, in my mind, the other experiment that I would like to do is to remove it from the substrate, because the Kondo effect, of course, comes from the coupling to the substrate. So that to me, that would be the best thing. For example, well, I guess the best thing, and this is what we wanted to do, Alex, is to actually take this nanoribbon and put it onto sodium chloride. Mm-hmm. You know, and that's something that we tried to do and failed. We were unable to do it. That would be a way to to distinguish between these two interpretations, because, you know, if you have two theories, they give identical answers. You know, it's just hard to distinguish them. You need to do another experiment. And so, you know, if we could put this nanoribbon here on the left onto sodium chloride, and then we could really see, you know, if that electronic structure, by decoupling it from the substrate, that should kill the Kondo. And then if this peak still remains, then we know that it's a narrow band effect. But if the peak goes away, then we would know that it's more of a Kondo effect. So I think that we need to do additional experiments to really unambiguously distinguish between those two interpretations.
Yeah, that would be fantastic. I have another quick question. So you said that like this GNR kind of stemmed from those like topological ideas, right? And I remember that in one of the like previous Muri meetings, you had a wonderful presentation where you kind of tried to explain the Lewis paper in a like simpler, like intuitive terms. And we were basically showing that like if you're coupling two different ribbons, you may or may not create kind of like radical states at the interfaces, depending on how you cut like single and double bonds, right? Like I think you remember.
Yes,
that.
of course.
That was actually really great because it kind of gave an intuitive way to think about it.
I know, and I never wrote that paper. Shit. No, but
right.
You can ask a question.
Yeah, but my question is that in a sense, that presentation kind of tied the idea of the topology to the like radical states, right? And I kind of see that nowadays, like there are barely like any papers which like refer to the like that Louis PRL's paper, right? And instead, people just use the Leib's theorem and also kind of count, you know, the sublattice imbalance and kind of count whether they are or they are not radical states. I'm kind of confused. Like, basically, are these two approaches point at the same thing technically, or like there's a difference?
I think that they are the same thing. I think that you can make a very beautiful connection, you know, between these different ideas. I don't want to the problem with the Steve Louis, you know, was the first person to, you know, think of, or him and his students and postdocs were the first people to think of topology in the context of nanoribbons, you know, so, you know, they really get the credit for that idea, which was done before the experiment. But it's hard, you know, it's hard to understand. And, you know, I think that there's, and those ideas, I think, haven't filtered strongly into the chemistry community, you know, and that's one of the problems. And, you know, but Stephen Louis and his guys and other people, other groups have pushed those ideas even further. So, you know, they have very sophisticated ways of understanding the electronic structure of these nanoribbons in terms of topology, and they're beautiful and they are powerful and quite useful, but they're hard and confusing, you know, for people not well versed in that really subtle, you know, band structure terminology. But I think that there is a very beautiful way to connect these ideas, which is, you know, there is a nice way to, because the point is like, how do you think about it in real space? You know, in my mind, it's always, you know, the chemists always think about everything in real space, and the physicists are always doing everything in Fourier space. And it's sometimes very hard to connect those things. And so in my mind, a very beautiful way to connect the ideas is to use the Wannier centers, you know, because if you take the band structure of a one-dimensional object, then the Wannier, if you do a Fourier transform of the band structure, then you go into this real space formulation and you get these Wannier centers, which is sort of telling you where the charge is located in the unit cell. And the Wannier center formulation is kind of confusing because the Wannier centers are not energy eigenstates. So it's like, what are these Wannier centers? They're not energy eigenstates, but they're more like where the charge is located. But it's like a reformulation of the band structure. And there's this really beautiful way of looking at it where if you consider the Wannier centers are located in the same place as these this simple bond pattern. What do you call it again, Alex? The name is escaping me.
It's radical states. Or...
Yeah, no. But when you do this little Kekulé drawings, and you are maximizing the number of
the Clark structure.
Yeah, the Clark structure, right? Right. And so, you know, it turns out that, you know, the chemists love the Clark structure. And so when you make a Clark structure, it turns out that where you put the double bonds in the Clark structure is almost always, and we actually showed this with calculations, when you make a Clark structure, the double bonds are always sitting where the Wannier centers sit. And so it turns out that there's this very beautiful connection between the very trivial Clark structure that chemists love and the Wannier centers. There's a connection. They're the same. And so in my mind, that is the key, because the location of a Wannier center is exactly equal to the Berry phase of a one-dimensional, band structure. The Wannier center expresses completely the topology. So all the topological information is in the location of the Wannier center. It's exactly one and the same. The location of a Wannier center is exactly equal to the Berry phase. It's this, it's really beautiful topological connection. And the location of the Wannier center is also almost always lies exactly where the double bond is in a Clark structure. And so in my mind, that's the connection, between all this topological stuff and this very simple chemistry way of thinking. And we were going to write a paper on that, but what happened is my student who really understood it the best, Dan Rizzo, graduated, and then the student in Steve Louis' group who calculated all the Wannier centers graduated, and I could never get them to write this paper. And also, of course, Steve Louis doesn't like it, because it's a little too hand wavy for Steve Louis. And so we never wrote that paper, really explaining that connection that I just mentioned to you. But in my mind, that is the key, because that completely connects all the fancy topology with just the simple chemistry way of thinking,
Thank you. Yeah, great speaker.
Yeah, that's great. Thank you so much. We've gone a little bit over time, but I just want to thank everybody who was able to make it to come to this inverse seminar. I think it's been really fun to have everybody here and to have all these great questions. And again, thank you to Dr. Crommie for agreeing to come and discuss his papers. So I guess I'll kind of officially end the time here, but I suppose I'm going to keep the Zoom open. So if anybody,
yeah, Mike, this was really awesome. It was really great to hear the stories behind the papers, which is something that you don't get when you read the papers. I mean, you read about the great science, but you don't know about the serendipity and about the insights and the all the things that lead to real science. And I think that was one of the things that we learned in the first experiment that we did in my group, and I feel like it was reproduced here. So and it's really been great having this conversation with you.
Thanks. It's been a lot of fun. It's it's like talking about your children. Everybody likes to talk about their children. So same thing with results.
But yeah, again, thank you everybody for coming, and again, thank you to the presenters too who presented. It's really great. So appreciate it.
Thanks a lot, guys. That was a lot of fun.
Yeah, thanks, Mike.
Thanks, Mike.
Bye-bye.